I'm not a fundamentalist in any of the normal ways, but I'm a fundamentalist in trying to respond to the title given to this session. So I'm going to take a very different approach and sort of do this from the biology angle, our assumptions about life in ET, which to some extent I think is another way of asking the question, are there laws in biology? Is evolution predictable? Are there certain things? Because we're making those assumptions when we talk about looking for extraterrestrial life, and certainly extraterrestrial intelligence. We're predicting that they may use radio waves or vision or different parts of the electromagnetic spectrum. And I'm going to pull it back off that I part and just the ET part and say where can we actually look for some commonality and make some predictions, because without that we really don't know what we're looking for. So in some sense it's saying, is biology a science in that there are predictions and so on, like in physics and chemistry. And so I'm going to try this in at least one different way, and if there's time I'll try in a slightly different way. But this is sort of one of the stump slides I give all the time. What do we need for life? And here's sort of the usual things that you see, biogenic elements. And what we mean here is carbon, hydrogen, oxygen, and we talked about that yesterday with all the pictures of the astronomers' periodic table, which is great comfort to those of us who are not brilliant in chemistry to be able to simplify it down to 4 or 5 elements. We certainly use nitrogen all over in our proteins and our nucleic acids and so on, and in fact without nitrogen we basically have a sugar world and fat, and I realize that many of the teens today are approaching that sugar-fat world, but for many of us we still cling on to nitrogen, sulfur, phosphorus. We also use things like sodium, magnesium, and my cosmology friends and stellar evolution friends say, you sort of get those as a bonus. If you're going to get the carbon, you're going to get a little of some of these others, so not to worry. And so the argument is that there's a great abundance of carbon, as was mentioned yesterday. It's extremely versatile chemically. Silicon, I guess, would be the runner-up, but as Lou Alamanoa points out, we're sitting on a large silicate rock, and although many of us have secondary brains, and still at this point secondary brains on the desks based on silicon, the rest of us are based on meat, and will be for a good long time. So we're back to the carbon, nitrogen, oxygen, and so on. So it has this chemical versatility. It has sort of the right middle level of stability. Carbon compounds don't break down in seconds, but they are stable long enough to have a biological time scale, but they're not stable basically forever as some of the silicon compounds are. And then finally, to me, the discoveries in astrochemistry have just completely stunned me. The fact that when we look out into the universe and we see these sorts of molecules out there that don't look unfamiliar to someone who's waded through a biochemistry class, it says, maybe the fact that we're talking about the sort of biochemistry, the core metabolism that life on Earth is built on, is not because of a lack of imagination, but this is actually the language of life in the universe. I tell my students, the stunning conclusion is that there may be students sitting on a planet around Alpha Centauri using exactly the same biochem book that you had to use this semester, except an Alpha Centaurian. I mean, if that isn't incredibly depressing. But, but what it does do is I don't know whether it was Stryer or Leninger, honestly. But the point is that you can now start to make some predictions if you buy my argument that life is going to be based on organic carbon. And again, I see these arguments, so you can actually predict an enormous amount from there. And that's why I made the comment yesterday that I thought that the Viking experiments were right on, looking for carbon exchange, because that to me is sort of ground zero for life, is the organic carbon. So we'll start with the biogenic elements, but then if you're going to do some chemistry, you need a solvent. And of course, liquid water is our favorite one for many reasons. There's plenty of it in the universe. Again, it was mentioned yesterday. And it's got all sorts of chemical properties that make it appealing. And if you have liquid water, it implies certain temperature and pressure regimes so that you can keep it liquid. But perhaps there are other solvents around. And what is really pushing us in this direction is Titan. Because here's the one other body in the solar system that is just full of organic compounds. I sort of picture the surface of Titan like someone went through a chemical closet at a university and just started smashing bottles. It's just got lakes of organics, much more than we have here. And so we very much want to see that as a potential other solvent, maybe liquid methane and so on. I think everyone here, nearly everyone here, remembers when the Huygens probe landed on Titan a few years ago, and I show this picture because it looks so so foreign and yet so familiar in some ways. And of course, I'm being incredibly nasty to you because that was actually Titan. This is a digital rendition of landing at O'Hare Airport, because every time I see this picture of Titan, it's O'Hare without the buildings, and here it is with the buildings sort of pixelated. So I got away with that at Berkeley in the astronomy department, so I'm feeling very good about this. Anyway, so we've got the biogenic elements, we've got the solvent, and we'll say it's liquid water, but it could be something else, perhaps. You need a source of energy, and I don't think we have any trouble imagining sources, solar sources, of course, geothermal and so on. Solar is a very obvious one. We talk about needing some kind of solid surface. You need some sort of way to concentrate these materials, whether it's in maybe in an icy body where you've got a dehydration reaction, so you're concentrating the organics, or maybe you're doing it on a clay surface in a meteorite, something like that. But we sort of in general have this feeling that because we need a long-lived body at a certain temperature and pressure, that we're talking about some sort of planetary or lunar surface. And then we need time, and this is batted around, and this is something that's bothered me increasingly over the years. People say, oh, well, you know, you need billions and billions of years and all that sort of thing. Well, the more we learn about the very early Earth, the more we realize that there was probably a liquid water surface within 200 million years or so after the formation of the Earth. And there's actually nothing that really stops life from forming very early. We just don't see it in a fossil record, either chemical or morphological, till after the late heavy bombardment about 3.5 plus 3.8 billion years ago. But there's good evidence that life could have arisen much earlier and made it through that late heavy bombardment, and that the problem with not finding it is just simply a matter of not having those rocks present. So we have this sort of Cliff Notes version of the evolution of life, the formation of the Earth, and then going through, and you've got the origin of life perhaps down here, perhaps a little bit later, and then you have this great age of microbes, and then at the very top, in very rapid succession, the origin of the great multicellular groups going, you know, from everything from jellyfish and starfish to plants and dinosaurs and so on. And you know, I get paid to put the NASA logo as the very pinnacle of evolution on Earth. The Stanford one I just throw in gratis. But the problem is that, and I think this came up yesterday, well, we need to have a star that will allow a planet to be there for X billion years. Well, try to think of this narrative as like a novel, and you know, if we only had one novel as an example of all novels, you know, War and Peace, Alice in Wonderland, take your pick, and then you'd say, well, you know, therefore, extrapolating from this, all novels have to have 30 chapters, and it has to be like this and that and the other thing. You would have a very biased view. And so to me, as I mentioned yesterday, the fact that it took so long for the great multicellular groups to arise, maybe because it has to, and maybe it's just because we're focusing on this one narrative and for some reason it didn't happen. So I'm not totally hung up on that. So I'm going to try one other just little approach. So we tried this sort of, oh yeah, we need the elements, we need this, this, and this. So let's step back a second and say, what do we need for life from another point of view? Well, we assume that you need some sort of physical body, likely to be based on organic carbon, and therefore the top priority of this body is going to be to exchange organic carbon with the environment, because you're fighting entropy all the time, as Schrodinger reminded us. You need some kind of survival. You have to deal with the fact that the environment's probably changing either faster or slower, so you may need some sort of physiological, morphological, or some sort of informational response to this. You need to leave offspring, because otherwise you're a total Darwinian failure. I won't, you know, mention names in this room, those of you who are already total Darwinian failures, but that's the name of the game in evolution. You need offspring, you need some sort of continuity, because your body presumably can't flick on and off. So that seems non-controversial, but every one of those you can say sort of but. Things like cellular slime molds form fruiting bodies when they're ready to produce. You know, are the individual amoeboids the cells, the organisms, or the fruiting bodies? You need to survive, but how long do you actually need to survive to count? I mean, E. coli divides every 20 seconds. If you had a life form that only existed for 10 nanoseconds, would you say, oh, sorry, you know, it's got to be 20 minutes by the E. coli rule, you don't count? I mean, you know, I'm trying to sort of take these arguments to the absurd here. Because we throw these words around. Leave offspring. Well, again, what about non-reproducing members? They're the classic example is, what about mules and so on? They're not leaving offspring. Does that mean they're not alive? Obviously not. And some sort of continuity. And I, point this out many times. I didn't know maybe 2/3 of the people in this room before Sunday night or yesterday, and there's still some people I don't know. So I really have no proof that you have a history earlier than Sunday night. For all I know, the telescope here has a little side business in producing astronomers so that they can get a constant business. I have no evidence for that, but I look around the room and everyone here is acting in a way that I'm going to give credit for being alive. So the question is, does it really matter whether you were produced by some nefarious operation that, Jay is really running in his spare time out back, or that you actually had parents and grandparents and can trace your ancestry back to the primordial ooze, the way it was pointed out by Gilbert and Sullivan. So these are sort of two approaches to looking at the life part, and I think this sort of helps to challenge what we're looking at in terms of life in general and even intelligence. And I'm going to stop there and pass it over to Kathryn.
Do you want to take questions first?
Oh, yes. Anyone like a question? Well, it's only going to make me match my sweater. What?
Just a challenge to one of your assumptions, because, and I don't know if it's a real challenge or not, but there's this new organization, the Center for Chemistry in the Universe, that in its propaganda for its own existence points out that our understanding of chemistry is limited on Earth because it's mainly in the liquid phase, whereas certainly in the Milky Way you have gas phase and surface chemistry reactions. Do you need a solvent?
The problem with doing the gas phase is that I think you have an issue with being too diffuse. And that was something that even Darwin worried about. You have a prebiotic Earth and you start to make or chemical compounds and they immediately get diluted in a global ocean or some sort of large ocean. And so I'd be very concerned that in a gas phase that you don't have the concentration, that you need some kind of solid substrate or some sort of evaporating liquid to get a sufficient concentration. But I know there is a chemist in the room who can answer that better than I.
I think in the gas phase in the interstellar medium, at some point, as you get more and more complex in chemical complexity, it gets so diluted because the gas is just not very dense. So you may be building up more complex molecules that could eventually lead to life, but every reaction that builds an even more complex molecule leaves you with fewer and fewer of each type in abundance in that gas. So it's very hard to build up past a certain point in complexity that has any significance relative to the bulk gas without some sort of condensed phase chemistry. So I think at some point the chemistry relies on a condensed phase network to be able to build the complexity that you would need for
But
life.
the surface of a grain is not a solvent.
Right, the surface of a grain is not a solvent. It is not clear yet what kind of chemistry can be supported on that sort of surface, and certainly temperature dependent as to
But I'm just playing devil's advocate here.
Yeah,
That's
yeah.
a way that we could go.
Right, right.
That could be a meeting place.
But looking at it from a chemistry perspective, at some point I think you have to have something like a meteorite or a comet or a planetesimal to continue on with the complexity argument for anything that's biologically relevant.
Thank you. I think we're saying the same things if you put it much more eloquently. Thank you very much.